Hello students, welcome back. Now in this part I am going to tell you about the different theorems on derivability or differentiability, and also I am going to tell you about what can be the reasons if a function is not derivable. So we will talk about all this through examples and we will talk about all this through different concepts, right? So let's start with the video. Okay, so now let us talk about some theorems which are related to differentiability. Okay, so let us start with theorem number 1. So theorem 1 says that if a function is derivable at x equal to a, so let us assume that there is some function fx which is derivable at x equal to a, then f is continuous at x equal to a. So it says that, first theorem says that if a function is derivable at some point, then it will also be continuous at that point. Okay, so if a function is derivable, it will be continuous. Now let us see the proof of this theorem. So proof of this theorem is written here. If f is derivable implies what? If f is derivable, I can say that f dash a will exist, right? Because if a function is derivable, then its dy by dx will exist, right? And this is nothing but dy by dx only. F dash a, it is a style of representing. Okay, so f dash a means dy by dx at x equal to a. Now we can say that f dash a exists, right? And if f dash a exists, I can say that this limit will also exist, because what is this? This is nothing but right hand derivative, right? So right hand derivative will also exist and it will be equal to left hand derivative, and this will be equal to finite. This is the definition that we have studied, right? So if f dash a exists, then this limit will also exist. Now let us consider this value, f of a plus h minus f of a. Right, now if I consider this value, now in the next step what I am doing is I am dividing and multiplying by h in this quantity. Okay, so first I am considering this quantity which is f of a plus h minus fa, then dividing, multiplying by h, and then taking limit both sides. Now I am applying limit on both sides, so limit here also and limit here also. So I am applying limit both sides in the next step. So this is limit h tending to 0, right? And limit h tending to 0. So limit h tending to 0, this will be, and this quantity is finite, this limit is finite. This is some finite value which is equal to f dash a, right? This limit is nothing but f dash a into h, and this h is tending towards 0, right? So into 0, because this h is tending towards 0, so this is a fixed finite number multiplied by 0. So finite number into 0 will be nothing but 0. So this limit is equal to 0. If this limit is equal to 0, I can say from here that limit h tending to 0, f of a plus h will be equal to f of a, and this is nothing but RHL. So I can say RHL is nothing but RHL is equal to f of a, right? Now if RHL is equal to f of a, then what can I say? If RHL is equal to f of a, then I can say that the function will be continuous. Similarly, I can take LHL and prove it, right? Here I took RHD, so I started with RHD, so I got RHL. So if I start with LHD, I will get LHL. So this will be equal to LHL also. So LHL equal to RHL equal to the value of the function, and which is equal to finite, so this will be continuous, right? Because this value exists, so this value will also exist. So if a function is derivable at x equal to a at some particular point, then that function will also be continuous. Okay, this is the first theorem that we have to remember. Okay, now there are 4 theorems in continuity to this, right, which are related to each other. So first one we have already seen the proof. Now for the next 3 I am not going to tell you the proof, but it is obvious, right? If a function is differentiable, it will be continuous. It will definitely be continuous, right? If a function is derivable at x equal to a, then it will be continuous also, right? So derivability implies continuity. If a function is derivable, it will be definitely continuous. But if a function is continuous, then we cannot say surely that that function will be derivable also. So continuity does not imply derivability. Okay, so you have to remember this that if a function is derivable, then it will surely be continuous, but if it's continuous, then we cannot say that it will definitely be derivable. Okay, now the third theorem is if a function is non-derivable, then we cannot say that it will be discontinuous also. If a function is non-derivable means dy by dx does not exist. Okay, if dy by dx does not exist, if it is non-differentiable, then we cannot say that it is non-continuous also. But if a function is discontinuous, right, there is a break in the definition of the function, we have to lift the pen. If the function is discontinuous, then it will be obviously non-derivable, right, because we have to lift the pen. So LHD will not be equal to RHD, right? Left hand slope on the left side will not be equal to slope on the right hand side. Okay, so it will be definitely non-derivable because there is a break, right? So if it is discontinuous, it will surely be non-derivable. But if it is non-derivable, then we cannot say whether it will be discontinuous or continuous. Okay, so we have to remember this 4 Guru Mantras, right? Every time, each and every time, whenever you are dealing with this chapter, this will always come, right, related to the question. This is favorite according to the examiner's point of view. Okay, so you can just remember it like this, that if a function is derivable, it will be continuous. If it is continuous, it does not imply that it will be derivable also. If it is non-derivable, this again does not imply that it will be discontinuous, right? Discontinuous I am just denoting by D bar, or you can just write it as discontinuous, right, C bar. And if it is discontinuous, this again implies, right, if a function is discontinuous, right, there is a break in the definition of the function, then it will surely be non-derivable also, right? So you have to remember this 4 theorems by heart it. Okay, it will be very much used in the questions. Okay, now let us go to the next slide. Now let us try to figure out what are the reasons of this non-derivability, right? Now we are saying that whether dy by dx does not exist, right? What are the reasons for this? Why dy by dx does not exist, right? What are the prime reasons which govern that dy by dx is not existing, due to which the function has to become non-derivable? Okay, so here are 3 main reasons why a function is non-derivable, right? So first of all, to look at this, let us understand when a function is derivable. A function is derivable, this we already know, right? The function is derivable if left hand derivative is equal to right hand derivative is equal to finite, right? If this condition is violated, then it will be non-derivable, right? If this condition is satisfied, then it will be derivable. If this condition is violated in any manner, then it will be non-derivable, right? So first thing is, if there is a sharp corner, right? Now what do you mean by sharp corner? Sharp corner in the graph of the function, right? So suppose the graph of a function is like this. Suppose the graph of a function is like this. This is the point x equal to a. This is x equal to a, this point. Okay. So here there is a sharp corner, right? Suddenly it was going down, right? It was decreasing, and suddenly there is a sharp corner and it is now increasing, right? Before a it was decreasing, the graph was going down, and suddenly it is going up now, right? So there is a sharp corner. You can see the graph of mod x. Mod x also has a sharp corner at x equal to 0. It was going down and suddenly there is a jump, there is an increment, right? Suddenly it started increasing. So there is a sharp corner, right? So this is a sharp corner that I am talking about. Suddenly it was going down, or it was going up and suddenly it is going down. It can be reverse also, right? It can be like this also. The graph can be like this also. It was going up and suddenly now it is going down. So this is called sharp corner. Now in this case you can see that what is left hand derivative? Left hand derivative will be this slope, right? Slope at x equal to a minus. So slope on the left hand side you can see that it will be negative, and the slope on the right hand side, so this will be the value. The slope of this tangent will be equal to nothing but left hand derivative, and the slope of this tangent will be equal to right hand derivative. In this case obviously LHD will not be equal to RHD. If there is a sharp corner, LHD will not be equal to RHD. Suppose if I take the graph of y equal to mod x, in this case what will be LHD? LHD will be slope of this line, right? So this is y equal to minus x line. So slope of this line is negative 1. So in this case LHD is negative 1. Left hand derivative is negative 1. And slope of this line, this is y equal to x line. Okay, so slope of this line is nothing but positive 1. So right hand derivative is plus 1, left hand derivative is minus 1. So obviously left hand derivative is not equal to right hand derivative. So this will be a non-derivable function. Okay, and there is a sharp corner. Okay, so wherever LHD is not equal to RHD, this is the first reason. Second reason is if the graph is discontinuous. I told you, right, the fourth one in the theorem. In the theorem we have seen the fourth result, which is if a function is discontinuous, it will definitely be non-derivable. Okay, so if a function is discontinuous itself, right, there is a break, there is a discontinuity, there is a break in the graph, then it will be surely non-derivable, right? And the third and the last thing is if LHD or RHD goes to infinite. I have repeatedly said this, that LHD equal to RHD should be equal to a finite quantity. If it is going to infinity or minus infinity also, right, plus infinity or minus infinity, then we will say that the function is non-derivable, right? If any one of this, LHD or RHD or even both, right, LHD, RHD or any one of this, either of this or both goes to infinity or minus infinity, then in that case we can say that the function will be non-derivable, and in those cases we can say that a vertical tangent exists. Vertical tangent means the tangent line will be vertical, right? So slope is infinite. So suppose I can have a graph like this. Suppose the graph of some function is like this, S shaped, right? So this is the graph of some function, this is x-axis, and suppose this is somewhere here, there is y-axis, this is x-axis. So here at this point, if I see at this point, I will get what will be the slope of the tangent. Slope of this will be the tangent, and slope of the tangent will go up to infinity, right? Slope of this line, a vertical line. Okay, so vertical tangent will exist. If a vertical tangent exists, then there LHD or RHD, okay, the slope on the left hand side or on the right hand side will go up to infinite. And if LHD or RHD is going up to infinite, then we can, in that case, we can say that a vertical tangent will exist. This is the vertical tangent. If a vertical tangent exists, then also the function will be non-derivable. Okay, so there are three main reasons which you have to remember. First is sharp corner. Okay, suddenly there is a change in graph. Second one is discontinuity, right? There is a break in the graph. And third one is a vertical tangent exists. These are the three main reasons why any function may be non-derivable or non-differentiable. Both are the same things. Okay, now let us see this example. Now for this example, we have to say whether this function is derivable or not, and if this is not derivable, this is non-derivable at what points, right? We have to check about the derivability of this function. Okay, so suppose this is sine of mod x, right? So sine of mod x. So if I try to find out the difference, what is the graph of y equal to sine x? Y equal to sine x will be like this. This is the graph of y equal to sin x, mod of sin x, right? Now if I try to plot the graph of this function, now this function will be nothing but this function will be, this mod will open in positive, this will be sin x if x is greater than or equal to 0, and it will be minus of sin x if x is less than 0, right? So for the right hand part, wherever x is greater than 0, there the graph will be same as the graph of sin x. Okay, so if I try to plot the graph of this function, sine of mod x, it will be same for x greater than 0. So for x greater than or equal to 0, it will be same as the graph of sin x, right? Because this graph is sin x for x greater than or equal to 0. For x less than 0, it will take the graph of minus of sin x. So if this is the graph of sin x, what will be minus of sin x? Minus of sin x will be opposite, like this, right? So here the graph of minus of sin x will be like this. So graph will be like this. This is the graph of y equal to sine of mod x. So you understood how to plot the graph of mod, right? Wherever there is mod, you just open it by taking the definitions, right? Once you take this as greater than 0 and once you take this as less than 0, and then you open it mod. Once you open the mod, everything will be clear to you, right? Wherever you see mod, just open it, right? Then everything will be clear. Now this is the graph of f of x. If this is the graph of f of x, directly from the graph clearly we can see that at x equal to 0 there is a sharp corner. Okay, it was decreasing and suddenly now it is increasing. So there is a sharp corner. So this function will be non-derivable. This function will be non-derivable at x equal to 0 because what is the reason? The reason is there is a sharp corner. Understood? So I hope this is clear to all of you. So students, I hope all the theorems related to differentiability are clear to you, and also now you have an idea what are the reasons for non-derivability or non-differentiability. Now in our next part, I am going to tell you about how to differentiate or how to encounter whether a function is derivable or not with the help of actual differentiation. So do not forget to watch the next part for that. Stay tuned on askIITians.com.